Let's talk about the OSI model. OSI is Open Systems Interconnection, and it's a conceptual model that you can build essentially any kind of network for. So it has 7 layers, and we typically draw it as a pyramid because, like a pyramid, you have to build from the bottom up. So down here you have your physical layer. If the physical layer doesn't exist or isn't working, it really doesn't matter whether the layers above it are working, because since you have to build from the bottom up, you can't start building bricks here because they'll just fall down. So we need to put these in the right order. So there is a nice mnemonic you can use to remember this. Please do not throw sausage pizza away. Ridiculous, but hopefully easy to remember. So we start off with the physical layer, data link, network, transport, session, presentation, and application. Now, network guys don't actually care about all 7 of these. We typically stop right about there. As a network administrator or network engineer, you're going to be looking just at physical, data link, network, and transport. Up here, this is all software. So application, you have things like Chrome, for instance, or HTTP, which is where you get web pages delivered. In fact, there are other models besides the OSI model. The one that we might really want to concern ourselves with is the TCP IP model. And the TCP IP model groups these top 3 into one big application section. In fact, we can see it right here. So on the right, here's our OSI model. Please do not throw sausage pizza away. And you can see how that maps to the TCP IP model. So the top 3 here all become one big application layer. That's because really most of the time applications take care of their own session and presentation. So if we start here at the bottom, notice physical and data link are also combined into one big network interface on the TCP IP model. Network becomes internet, which is kind of interesting, and transport stays transport. So now we need to know what these layers do, and we're really just going to worry about these bottom 4. So down at the physical layer, at the very bottom, physical layer includes things that are physical properties, things that carry electricity, for instance, or wireless radio waves. Those are all physical properties. So we have cables. If you have a network model that includes cables, so here's a switch, and let's say off of that switch you have a few hosts. So these are just computers hanging off a switch. If this line right here goes down, this cable breaks, this guy is no longer online. His network has been severed. So it doesn't matter whether his IP address is correct or whether Chrome is installed. If that cable doesn't work, the whole thing falls apart. So that's why physical layer cables are at the very bottom. We also have things, as I mentioned, like electricity, or if you're using fiber optic cables, then light, or if you're on Wi-Fi, then radio waves. These are all physical properties. So if the radio waves aren't propagating or you're too far from your wireless access point, it won't matter that you have an IP address. Your physical property has gone away. Now, not all hardware is down at the physical layer, which is a unique thing when you think about it, because a switch is a physical thing. It's a thing that you can see and touch. But it's not designed to work at the physical layer. It's designed to work at a different layer. So as we move up from physical, we're going to go to data link. And this is kind of a weird layer. I think the next layer, network's a little easier to understand. So the data link layer includes MAC addresses and frames. So a MAC address or media access control is a special kind of address that comes built into your network interface card. So let's say that you have a computer. So here's a desktop computer, and at the back of it, you've got all your ports, and right here is your network port. This network port is built by whoever made the chipset for your motherboard or for your network card. So let's say you have a Dell computer, and Dell didn't actually make the motherboard themselves. So let's say they bought it from somebody else who included chips for the network card from Broadcom. So Broadcom is a maker, a major manufacturer, in fact, of some of these networking chips that go on the motherboard. So the MAC address is actually assigned by Broadcom during the manufacturing process, and it can never change. Now, that's not to say you can't spoof it, you can't make it pretend it's something else, but this address is burned in from the factory to that network interface. So a MAC address looks something like this. It is hexadecimal, so that's 0 through 9 and A through F. 2, 3, 4, 5, 6. There we go. And it is 48 bits. So we break it down into 12 hexadecimal characters. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, I've got them all. And what we're going to do is break this address in half. You got the first half, you got the second half. The first half will tell you who built that networking device. So there is a governing body that hands out these first half of addresses. So let's say we're still dealing with Broadcom. That organization might say, all right, Broadcom, you can use 0DCA10, and all of your stuff has to start with that, or until you run out or request more, and then we'll give you another one. So Broadcom might have several of these, but there's a master list. That means if you know a MAC address, because you can see it, you know who built the thing. The second half of the address is up to, in this case, Broadcom to make up. And they could do this in serial, so they could start with 000000, and that's the very first card off the manufacturing line. And the next one is 1, the next one is 2, and so on. Or they could have some other algorithm. Now, the goal of this is to create unique addresses. Every MAC address in the world should be unique. However, problems occur. There have been mistakes. So if Broadcom has this front half and they're responsible for making the back half unique, they should be unique throughout the world. Now, I mentioned this is a 48-bit address. So how many different combinations are there? Well, we can figure that out because we're working in binary here, as we always are in computers. We take 2 to the 48th power, and that gives us our total number of addresses, which is approximately 281 trillion. Now think about how many networking devices there are in the entire world. Every computer ever built. Laptops have an Ethernet port and a Wi-Fi card, and so that's 2 MAC addresses for every laptop. Now, 281 trillion may not actually last forever. We might exceed that number at some point, so we have to bear that in mind. So also down here at layer 2, on the data link layer, we have frames. And a frame is a container for data. So let's actually back up a little bit to the physical layer. Down here at the physical layer, if we want to transmit data over a regular UTP Ethernet cable, that data has to come in electricity. It's electrons flowing down the wire. So imagine that we're doing those electrons, right? So here's electrons, and then here's not some, and then here's some and not some. So they come in some pattern that makes it binary. So this is going to be 1, 1, 1, 0, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, 1, 0, 1. So there's the pattern of binary coming down the wire. That's all that happens on the physical layer. When we move up to the data link layer, we create a frame. What we do is we take that data and we perform an action called encapsulation. We encapsulate the data by adding some fields, some extra data to it. So at the front, we're going to put the source MAC address and the destination MAC address. And on the back, we're going to put the cyclical redundancy check. This is just a check that says, I am a result of some action that's happened on this data, some algorithm. And If I redo that action when I get to my destination and I don't end up with the same result, something happened here to this frame. Something didn't get sent correctly, and I know to discard it. So it's just a check to make sure that the data came in accurately. So we have our binary data gets encapsulated into a frame as it moves up this way. So switches deal with frames. If we talk about switches and hubs, we're going to draw them like this. So they are a square with an X through them, gives you a switch. Switches and hubs do the same job, but they do it very differently. Their whole goal is to allow devices, computers, to talk to each other on a network. So here's 3 computers. We'll just label them A, B, and C. If A wants to talk to B, it can do so because it has a connection through this switch. So the data moves down the line, the switch receives it, and the switch says, all right, where does this go based on the destination of this frame? I see that it's going to B because it has B's MAC address listed. So then it just sends it out via the port to B. Now that's what a switch does, and a switch can do that because a switch keeps a table in memory of what's connected to it. So if you add a new computer, we're going to connect D. D is going to send out some broadcast information saying, hey, I'm new here, tell me about the network. Well, when it does that, it sends a frame with its own source MAC address. The switch receives it and it says, oh, I see that D has this MAC address, I'm going to remember that, and it puts it in the table. And now it knows that out port, whatever this is, let's say 4, D is connected with this address. So anybody that wants to talk to D, the switch can send that data down there because it knows that D is connected to it now. Some things, though, require broadcasts. They aren't bound for just one computer, they're bound for every computer. So let's say that A is sending a broadcast. The switch gets it and it sends it out to everybody except back to A, except back where it came from. Now that's a switch, and a switch is smart because it keeps that table and it knows what's connected to it. A hub, on the other hand, is connected largely the same way. So we'll do A and B and C, just like we had before. Now, a hub does not keep a table. A hub has no idea what's connected to it. So anytime data comes in from A hub simply sends it out every other port. If D is connected here, D will also get a copy of that data. So notice a couple of things. First of all, this is really inefficient. Every time a frame comes in, it gets sent out every other port. That's wasteful. Also, there's a security issue. What if A wants to send data to B like it did before, but that data should be private, that data should be secure? Well, C and D are going to get a copy of it over here on the hub, but not on the switch. Now, normally, computers are configured such that if information they receive is not actually meant for them, they simply discard it. So if D gets a copy of that message, it says, no problem, this isn't for me, I'll throw it away, ignore it. But it doesn't have to. We can configure it with software to say, log everything that you see instead. Keep track of it, keep a copy of it. So hubs are inefficient and insecure. So why do they exist? Well, they don't so much anymore. You can still find them occasionally, but by and large, switches have entirely replaced hubs. Hubs are a bus network. Now that you've seen your topology, remember that a bus, everything connects to a common line, like this. So that means if data goes down this wire, everybody gets a copy of it. That's exactly what happens in a bus. Even though it looks like a star from the outside, it's connected physically like a star, internally, electronically. All it does is repeat information out every port. It's electronically a bus. Now, a switch is actually a star. So this is the most common topology you're going to see in a wired local area network. So that's layer 2 with frames and switches. We move up to layer 3, and now we have our network layer. Network layer, we get IP addresses and we get routers. And we're not going to talk a whole lot about routers, but we are going to talk about IP addresses. You've probably seen IP addresses before. We've used them in class. IP addresses, there's 2 different kinds. We have IP version 4 and IP version 6. They both work on the network layer because they do the same job, but 6 is an update to 4 to fix some of the problems that we have. So let's start with IPv4. IPv4 looks something like this. It has 4 octets. There's 1, 2, 3, 4, separated by 3 dots or periods. Why are they called octets? Well, an IPv4 address is 32 bits. Every bit is 8, or every octet is 8 bits. So there's 8 bits of information here, 8 here, 8 here, and 8 here. 8 times 4 is 32. So octet, oct, like an octagon, is 8. So that's where that name is derived from. Octet, 8 bits per section. If we were to convert these numbers to binary, what we would find is we would have 8 bits, 8 zeros and ones per section. So 9, for instance, is going to be 0, 0, 0, 0. Let's see, that's 128, 64, 32, 16, 8, and 1. So that is 9 in binary. That's 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. If we do that here and here and here, we'll end up with 32 zeros or ones, giving us our 32-bit address. Now, this number can be subnetted or broken down into a lot of different formats. Typically what this tells you, though, is what other things are on your network. Now, you have to combine it with what's known as a subnet mask in order to do that. So let's say that we have a /24, which is 255.255.255.0. Now, don't worry so much about what those mean right now. What this means over here is that anything that starts 216.9.137 is on our network if we are a part of this, if this is our address. So .46 is part of our network. .111 is part of our network. .252 is part of our network. Anything that starts 216.9.137 is part of our network if this is our subnet mask. So in case of the school, we have something like 10.118 that we see pretty frequently at Hoosier Hills. So 10.118.2.46 is an address that we might see sometimes. Anything that starts 10.118.2 is going to be part of our network, but also, in fact, our network's a little bigger. Anything that's 10.118.0 through 7 is going to be part of our network. So our network's a little bit larger. So these are typical IPv4 addresses. There are some that are public and some that are private. So private addresses include 10.anything. If you see an address that starts 10. That's a private address. It is not routable. You can't get to it on the internet. You can only get to it on your local network. The same is true of 192.168.anything. That's private. This is the most common address scheme you're going to see in your home. So if you have a wireless router or something like that, it's probably on this network, 192.168.0 or 192.168.1. Those are the two most common addresses you're probably likely to ever see. There's a third private one. It's 172.16 through 31.anything. So this one's a little odd. 172.16, 172.17, 172.18, etc. are all private. Now you get up to 172.32, and now it's public all of a sudden. So these are the 3 private blocks. We can reuse these on any private network. The address that I showed you before, 216.9.137.1, is public. Now, this one I don't think exists right now, but this is an address that used to be assigned to a DNS server that I worked with. So I know that this one was public at one time. All of these public addresses come from a governing body. That governing body has to say, you're allowed to use this block of addresses for your public servers, and nobody else can, which makes them routable to anybody on the entire internet. So how many addresses are there? Remember, we're working with a 32-bit address. When we did this with MAC addresses, we took 2 to the 48th power because they were 48 bits. So we're going to do the same thing here. 2 to the 32nd power is about 4.2 trillion. Sorry, 4.2 billion. My bad, billion. So think about how many people there are in the world. We have about 8 billion people. That means there's not even one address to go around for every person in the world. Think about how many addresses you use in your home. So you've got one for your router. And let's say you've got, you and your siblings and your parents, maybe you each have a computer. So let's say there's 4 PCs in there, laptops or whatever. Maybe you've got one for your Xbox. You've got 4 phones, cell phones, all have addresses while they connect to your Wi-Fi. So there's 10 addresses that you're using in your household right there. So you're using more than your fair share. But in fact, these are all private under here. Your router is public. So in fact, you're only using one out of that big public pool. These are all private and these can be reused on everybody's network. So we've found a way to stretch this 4 billion addresses out. And for good reason. Think about how many addresses somebody like Google needs to use or Amazon. So we have run out of those 4 billion addresses, totally out. So that has facilitated the move to IPv6. So how big is IPv6? Well, that is a 128-bit address. It's huge. 2 to the 128th power is some number of undecillion. There we go, addresses. So how big is an undecillion? Well, let's go over here and we say there's thousands, million, billion, trillion, quadrillion, quintillion, sextillion, septillion, octillion, that's 3, nonillion, decillion, undecillion. So there's 100 undecillion, and we actually have a few more than this, but it's in the undecillions. There are this many IPv6 addresses available. That is a crazy large number that we should never, ever, ever run out of. We've run out of the IPv4, which is why we're up at IPv6, because we needed the extra space. So an IPv6 address, much like a MAC address, is drawn in hexadecimal. So if you remember, IPv4 was formatted like this. IPv6 is formatted like this. So what you end up with are sections of 4 characters, much like a MAC address, hexadecimal, 0 through 9, A through F. So you can see we have numbers here. We've got a D and a B and an A. We also have this weird double colon. So if I were to expand this out, what I'm actually going to do is make some sets of zeros here. There we go. There is a full IPv6 address. Notice how big that is. 1, 2, 3, 4, 5, 6, 7, 8 sections of 4 hexadecimal numbers. This is a much larger address than the IPv4 that we see up here. Now, IPv6 has some other characteristics besides just the sheer number or size. It's easier to subnet. It's easier to break apart into different networks. Which makes it much easier to manage for internet service providers and even for you in your home. So let's say that you get assigned to your router 2001 0DB8 ACAD000F, the first half of that address. That's what gets assigned to your router. And you can then make up anything you want for your own personal scheme over here. Now that might be true in your home, in your business, you name it. So even Microsoft with a huge network might only get assigned one of these IPv6 addresses. They then make up what happens over here. So how many is this? Well, this is some number of quintillion addresses. So you in your home get a few quintillion to use. Microsoft gets a few quintillion to use. Amazon gets a few quintillion to use, because this is more than enough no matter what type of network you're building. Everybody gets the same amount, which makes it really easy to dole these out because there are so many of them. So all of these addresses happen up at layer 3, the network layer, where we also find routers. Routers are what separate networks. So let's say that here is your wireless switch or wireless access point, and you have connected to it your phone and your Xbox, and maybe even have a wired PC to it like that. This is probably a router inside, or maybe it connects to a separate router, which then connects to your internet service provider. So let's say this is Comcast, or maybe it's AT&T, whoever you have service with. This router says, this is a separate network from this. This is Comcast's network. This is your personal network. Or maybe we have the same thing at the school. This is Smithville's network out this way, and this is the school's network this way. So this router separates different networks. The switches pull devices into an existing individual network. So that's the job of routers. And the last layer that we need to discuss is the transport layer. That's up there at layer 4. Up here we find TCP, UDP, and ICMP. TCP is the most important one for us to talk about. It is in fact spelled out in the TCP IP protocol. Notice IP we talked about on layer 3, TCP up at layer 4. So the TCP IP protocol, it's actually more than one protocol, and it even spans multiple layers. So TCP is what's responsible for getting information from one point to the other in order and correctly. So let's say you're going to download a large file. You're going to download a movie. So here's the movie. Here's the whole thing. And it's 1 gigabyte in size. It's a large movie. We can't just take 1 gigabyte and start breaking it into bits, right? Zeros and ones, and say, here you go, here's a stream of zeros and ones. Because what happens when a single 0 or 1 gets out of order, gets mistaken, doesn't arrive? The whole thing could be corrupt. We can't have that. So instead, what we do is we break it into bite-sized chunks. So we break this movie up into pieces like so. And we only send one piece at a time. So we're going to start with piece 1. We break piece 1 into bits. We encapsulate it into a packet. For layer 3, we put an IP address on it, which gets encapsulated into a frame at layer 2, which then finally gets converted into zeros and ones, into bits. And we send those bits down the wire. When they get to the other end, what we have to do is make sure they're right. And we have to make sure that all of those bits come in order. We don't have to send them in order. In fact, we could send part 1 and then part 3 and then part 2. But when it gets to the other side, we have to put it back together like a puzzle. That's the job of TCP, putting things back together. Its neighbor, UDP, or its cousin, doesn't do that. In fact, the whole point of UDP is just to be fast. So imagine this download comes in out of order or with missing pieces. It's not going to work, right? If this is software to be installed, if you've downloaded iTunes and you go to install it and it's missing pieces, it's never going to install. So it has to be exactly correct, bit for bit, when it reaches the other end. But let's consider a phone call that happens in voice over IP, like the phones we have in our classrooms. Imagine if whoever's speaking into the microphone, that data gets packaged up and sent, and it arrives, and some of it's missing, right? Packet 2 isn't there. Well, TCP would say, hey, resend me packet 2. Okay, thanks, here it is, now I've got it. And then it's gonna reassemble it. That takes time, and you're gonna end up with delays if you do that. But if you're in a phone call and you break apart somebody's message, meet me at the playground, something like that. And you drop the last part of meet, and you say, meet me at the playground instead of meet me at the playground. You would still understand them, right? If that's the packet that got dropped, no big deal. But if we had this big delay or things arrived, in weird orders, that's not going to work. So the whole point of UDP is not to get data there correctly, but to get it there fast. So something like VoIP that's using phone calls is using UDP, whereas downloads are using TCP. Those both happen at the transport layer on layer 4. So if we come back one last time, we see the OSI model here, physical layer with cables and electricity and light and radio waves. The data link layer, that's where we get our MAC addresses that are burned in from the factory and switches. The network layer is where we get IP addresses and routers. And the transport layer is where we have TCP that puts things together, or UDP that just sort of gets things there fast. We can compare that to the TCP IP model, which fits in with the OSI model very nicely. So we're going to mostly focus on OSI model with the understanding that the TCP IP model fits the OSI model pretty well. So that's your introduction to the OSI model.